Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Can you explain the concept of text-to-SQL and its importance in database interactions?
Text-to-SQL is a technology that allows us to translate human language queries into structured query language, SQL, which is the language used to communicate with databases. It is like having a translator that can understand what we say in normal language and convert it into a language that databases can understand. This is important because it makes it much easier for people to interact with databases. Instead of having to learn complex SQL syntax and write queries manually, users can simply type or speak their questions in natural language, and text-to-SQL technology will convert it into SQL for them. This saves time and effort, and makes it possible for non-technical users to access and retrieve data from databases. By enabling natural language queries, text-to-SQL technology opens up the power of databases to a wider audience. It allows business users, analysts, and even children to ask questions and get meaningful answers from databases without needing to understand the intricacies of SQL delve. This improves data accessibility and empowers users to make data-driven decisions more easily. In summary, text-to-SQL is a technology that bridges the gap between human language and SQL, making it easier for people to interact with databases and retrieve the information they need.
That's a great explanation. It's fascinating how text-to-SQL technology acts as a translator, converting human language queries into SQL language that databases can understand. This definitely simplifies the process of interacting with databases, especially for non-technical users. It's impressive that it enables natural language queries, making databases more accessible to a wider audience. This technology has the potential to empower users to make data-driven decisions more easily. I'm curious about the historical approaches that were used before language model-based models, LLMs, were introduced for text-to-SQL. Can you elaborate on that?
Before language model-based models, LLMs, were introduced for text-to-SQL, the historical approaches involved pre-processing user queries to match a specific template. These templates were then used to rephrase the user query. However, these templates were typically use case specific, meaning they were designed for specific types of queries and databases. This made it difficult to extend beyond those specific cases. Imagine you have a set of Lego blocks, and you want to build a car. But instead of using your creativity to build different types of cars, you have to follow a specific template that tells you how to assemble the blocks for a specific type of car. This means you can only build the cars that the templates allow, and it becomes difficult to build anything beyond that. Similarly, the historical approaches in text-to-SQL use templates that limited the types of queries that could be generated, requiring a lot of manual work and data preparation to fit the specific format and template. These limitations made it challenging to handle a wide variety of user queries and databases. It required a considerable amount of effort to adapt the templates for different use cases and databases. This approach was not scalable and hindered the development of more advanced natural language processing models for text-to-SQL tasks.
I see. The historical approaches for text-to-SQL relied on predefined templates that were specific to certain use cases and databases. It's interesting to think of these templates as limiting the creativity and flexibility in generating queries, similar to following a specific Lego car template. This approach required a lot of manual work and data preparation to fit the template and was not scalable for handling diverse user queries and databases. It's clear how this approach posed challenges and hindered the advancement of more advanced natural language processing models. With the introduction of language model-based models, LLMs, how have they improved the accuracy and efficiency of the text-to-SQL process?
LLMs have significantly improved the accuracy and efficiency of the text-to-SQL process. Before the introduction of LLMs, User queries had to be pre-processed to match specific templates, which were often use case specific and difficult to extend beyond that. This required a lot of data preparation and manual work. However, LLMs have changed the game. They have a vast knowledge base and context understanding capabilities, allowing them to generate accurate SQL queries directly from natural language descriptions. Their complex architectures and comprehensive data used for pre-training enable them to decipher complex relationships between words, overcoming many challenges of previous methods. In simple terms, LLMs are like super smart assistants that can understand and convert our everyday language into a structured language that databases can understand. They have learned from a lot of examples and can now accurately translate what we say into the language that computers speak. By eliminating the need for manual template matching and data curation, LLMs have made the text-to-SQL process more accurate and efficient. They have reduced the amount of time and effort required to convert natural language queries into SQL queries, allowing developers and organizations to streamline their data workflows and gain fresh insights from their databases.
That's impressive. It's fascinating to see how LLMs have revolutionized the text-to-SQL process by eliminating the need for manual template matching and data curation. Their vast knowledge base and context understanding capabilities enable them to accurately generate SQL queries directly from natural language descriptions. It's like having a super smart assistant that can understand and translate our everyday language into the structured language that databases understand. By leveraging the complex architectures and comprehensive pre-training data, LLMs are able to decipher the intricate relationships between words and overcome the challenges of previous methods. This not only improves the accuracy of the text-to-SQL process, but also enhances efficiency by reducing the time and effort required to convert queries. The ability of LLMs to streamline data workflows and provide fresh insights from databases is truly remarkable. It's exciting to imagine the possibilities that LLMs bring to the table in the field of text-to-SQL. I'm curious about the architectural patterns for implementing LLMs in SQL query generation. Can you provide some insights into these patterns and their best use case scenarios?
Certainly. The report outlines 5 architectural patterns for implementing language model for SQL query generation, LLM, in different scenarios. Pattern 1. Intent detection and entity recognition with text-to-SQL. This pattern focuses on converting natural language queries into SQL queries by first detecting the user's intent and recognizing the entities involved. It is commonly used in applications like chatbots, where understanding the user's purpose is crucial. For example, if a chatbot receives a query like find all the books written by author X, the intent would be to retrieve book records, and the entity would be the author's name. This pattern uses supervised learning models to classify intents and recognize entities accurately. Pattern 2. Query generation with template-based approaches. In this pattern, the LLM generates SQL queries by filling in the blanks in a predefined template. It involves constructing the SQL statement based on the provided template. This pattern is useful when there is a fixed structure or a limited set of query patterns. For example, a template could be used to generate queries for filtering data based on specific conditions, such as select HA from table where column AG value. The LLM fills in the necessary elements like table name, column name, and value to create the final query. Pattern 3. Error handling and self-correction. This pattern focuses on handling errors that may occur during query execution and self-correcting the queries. When an initial query execution fails, the LLM captures the error messages and uses them to modify the query. It iteratively refines the seed prompt by incorporating the error feedback, an incorrect SQL statement, until the query executes successfully. This pattern ensures that the LM continuously learns from its mistakes and improves its query generation capabilities. Pattern 4. Feedback-driven query refinement. In this pattern, the LM incorporates feedback from users or experts to refine its query generation process. It uses user feedback on the generated queries to understand preferences, correct mistakes, or improve the query's relevance. The LM adapts and refines its strategies based on the outcomes and feedback received, enhancing the quality of the generated SQL queries. This pattern is particularly useful in dynamic environments where the query requirements may change frequently. New Pattern 5. Hybrid approaches with rule-based systems. The last pattern combines the strengths of LMS with rule-based systems. Rule-based systems use predefined rules to generate queries, while LMS provide the flexibility to handle complex and ambiguous queries. By integrating these two approaches, it is possible to handle a wide range of query scenarios effectively. This pattern is suitable when there is a need for both precision and flexibility in SQL query generation. Each of these architectural patterns has its own best use case scenarios, depending on the specific requirements of the application. For example, Pattern I is commonly used in chatbot applications to understand user queries, while Pattern 2 is useful when dealing with fixed query structures. Pattern 3 and IV help in error handling and incorporating feedback to refine query generation. Pattern V is suitable when there is a need for both rule-based precision and LM-based flexibility.
Thank you for providing detailed insights into the 5 architectural patterns for implementing LLMs in SQL query generation. It's interesting to see how these patterns cater to different use case scenarios and address specific requirements. Pattern I focuses on intent detection and entity recognition, making it suitable for applications like chatbots, where understanding the user's purpose is essential. Pattern 2, involving template-based approaches, is useful when there is a fixed query structure or a limited set of query patterns. This pattern simplifies query generation by filling in the necessary elements based on predefined templates. Pattern 3, error handling and self-correction, enables the LM to learn from its mistakes and iteratively refine the query by incorporating error feedback and incorrect SQL statements. This pattern ensures continuous learning and improvement. Pattern 4 incorporates user and expert feedback to refine query generation, enhancing the quality and relevance of the generated SQL queries. This pattern is particularly useful in dynamic environments with changing query requirements. Pattern 5 combines the strengths of rule-based systems and LLMs, providing both precision and flexibility in SQL query generation. This pattern is suitable when there is a need for a wide range of query scenarios. These architectural patterns offer valuable insights into how LLMs can be effectively utilized in different scenarios, catering to specific requirements and enhancing the overall text-to-SQL process. I'm curious about the practical demonstrations mentioned in the study. Can you provide some examples of how LLMs and BigQuery were used in the travel and leisure industry?